So I thought today we would finish up the chapter on integrals. The next chapter will be on applications of integrals. And we've already learned a couple. We can find the area between a function and the x-axis. We can also find the average value of a function between two different values of the independent variable. But there's going to be a lot more that we find in the next chapter. So I've kind of asked you to just believe me that there are going to be a lot of applications of this signed area that we've been talking about. This chapter has been concentrating on finding the signed area. So the first thing we did, as you remember, is we took rectangles because we knew how to find the areas of rectangles. And the more rectangles we added up, the less error there was. But there was still some error. So we thought, well, we'll take an infinite number of rectangles. We took the limit as n approaches infinity, and then we were able to get the exact signed area. The problem was that the algebra was really hard even on simple functions, and on most functions it would not work at all. Then came the fundamental theorem of calculus, which allowed us to find this exact signed area, to take an infinite number of these rectangles and add them up, just by taking the antiderivative of the function and plugging in the two endpoints and subtracting them. So we were really excited about that. And then we even learned with U substitutions how we could do a lot more antiderivatives. So you might ask, then why in this last talk in this chapter are we going to talk about approximating signed areas again? And the answer is, even though it's a little bit sad, even with all these techniques we have of solving for antiderivatives of functions, there's going to be many functions that we can't take an antiderivative for. So we can't use the fundamental theorem of calculus if we can't take the antiderivative of the function. So it is going to still be important to be able to approximate. Not as important as it was back when Newton and Leibniz and Riemann, when they were doing it, then it was really important because they did not have the technology that we have today. So let's go and try to approximate the area between this parabola and the x-axis from 0 to 5. Now, we could do this in a lot of different ways. One way we did it already was with rectangular approximation methods. And when we did it, we always divided everything up nice and evenly. But you don't really have to. Like we could start here at 1 and go to the right. So from 0 to 1, I go as far to the right as I can. And 25 minus 1 is 24, so that has 24. And then we could go all the way over to 4. So we would have 24 times 1. Now in this one, when we plug in 4, we get 9 is our height. So we'd have 9 times 3 for the width. And then in the last one, we don't get any contribution. So altogether you get 24 plus 27, or 51, is an approximation for our signed area in here. Which, because it's above the x-axis, is going to be the actual area also in this case. But what could we do that would be better than that? Maybe we could use something other than rectangles that might give us a closer approximation. So let's stick with the same way we divided up, from 0 to 1, from 1 to 4, and 4 to 5, but let's use trapezoids instead of rectangles. So we're going to use these two sides as our parallel sides, and then we're going to use that bottom and go like this. And we're going to do the same thing here. We're going to use these as our two parallel sides, and then we're going to go like last one will go like that. So you can see all of this that we missed with rectangles, you're not going to miss as much with a trapezoid. So we've got 3 trapezoids. So the formula, if you remember from geometry, if you have a trapezoid, if you let the height be the distance between the 2 parallel sides, which we'll call the bases, the formula for the area is h over 2 times base 1 plus base 2. So in this case, we've got, because our trapezoids are on their side, the parallel sides are this way, so you kind of look to the side. So the first one is going to be the bases are going to be 25 and 24, and the height is just going to be 1, the distance between the bases. And then you have another one, this trapezoid, the height is going to be 3, that's the distance between the 2 parallel sides. And we're going to have 24 for one side, and then 9 for the other. And then in the last one, we have 1 over 2 times 9 plus 0. That last trapezoid just turns out to be a triangle. So altogether, you add them all up, and it comes out to be 78. I think that's a lot better approximation than our 51. So maybe trapezoids are going to work out pretty nicely. Now, more trapezoids, you get a better answer. And sometimes it's going to be easier if you divide it up evenly, unlike here where I divided it up not equally. So let's go to a general case over here where I have y equals f of x, and I'm going to divide from a to b up into n sections. So I'm going to call this x sub 0, x sub 1, x sub 2, and I'm going to keep going until I get up to x sub n. And I'm going to divide them evenly, so each one of these intervals is the same. So if that's true, when we do our trapezoids, what we're going to get, the height from here to here is always going to be the same. What is the height going to be? It's going to be b minus a, the total width, divided by n. So we have a way of getting h, and then the total signed area, which by the way is what? The signed area is the integral from a to b of f of x dx, is going to be approximately equal to h over 2. And then we know what the h is. Now, what's our first base? Right here, it's f of x sub 0. Well, just to make it easier to write, instead of calling this f of x sub 0, we're going to call it y sub 0. And then this next one, f of x1, is going to be the other side. We'll call that y1. So that would be the area of the first trapezoid. The next one is still going to be the same h, but now we're going to have y1 plus y2. And this is going to keep going. And then the last one, we're going to have y sub n minus 1 plus y sub n. So, can we simplify this? Well, every term has an h over 2 in it. And then what do we have? We have y0, and then we have two y1s. And then there's going to be two y2s. In fact, there's going to be 2 of every side. Even y sub n minus 1 gets used in this trapezoid and the one just before it. The last one only gets used in one trapezoid. So, if you take this together, we're saying that the definite integral from a to b, the signed area between the function and the x-axis, is approximately equal to this. And this is called the trapezoidal rule. So this is just a, we don't have to know this rule. We could just always divide it up into as many trapezoids as we want and just do separate trapezoid formulas. This just makes it a little bit easier. So say we go back to this problem and see, instead of doing 3 trapezoids, let's see if we do 5 trapezoids. Let's divide this up into 5. So then what would it be? H would now be 1. And the first side is 25. But then you'd have 2 of this next side, which is 24. You'd have 2 of the next side, which is, when you plug in 2, you get 21. Then when you plug in 3, you get 16. When you plug in 4, we know we get 9. And the last side we only have 1 of them, but in this case it's 0. So that's what the trapezoidal rule would say. When you add all this up, divide by 2, you get 82. Or some, I actually think this is 78.5 and this is 82.5. I'm just trying to remember back when I did it. Now, what would be the actual? On this one, we can actually find the actual. It'd be the integral from 0 to 5 of 25 minus x squared dx. So the antiderivative is 25x minus x cubed over 3. We can use the fundamental theorem of calculus. And 0 is going to give us nothing, but we get 125 minus 125 thirds. Well, that's 375 thirds, so altogether you get 250 thirds, or 83 1/3. So I'm pretty sure that was 82.5. So you can see a little bit that this is really close to the actual. Quite a bit better than just doing 3 trapezoids, but those trapezoids were a lot better than doing the rectangles. So quickly we should talk about these approximation methods. Are they overestimates or underestimates? Or does it matter with something? So what I did is kind of gave you the 4, besides straight lines, I gave you the 4 different ways curves could go between 2 points. So they could be concave up and increasing, concave up and decreasing, or both increasing. So what would a trapezoidal approximation do? On this one, well, I'll do all of them. Trapezoidal approximations, I'm just doing 1 trapezoid in this case, but it's going to be the same if you did a bunch. What do we see? With trapezoids, you're going to have your contributions are going to be above the actual in both cases here. Whereas in these 2 cases, the trapezoid, the area is going to be underneath the actual. So it has to do with the concavity. When it's concave up, trapezoidal approximations always over-approximate. When it's concave down, as we found in this one, which was concave down, they under-approximate. And as long as we're talking about approximations, what if they were right Riemann sums? What if you were doing rectangular approximations? Well, let's try the same thing here. If I went up and over, you can see I've got extra. Down here, if I went up and over, I'm missing some. On this one, if I went up and over, I have extra up in here. And on this one, if I go up and over, I'm missing some. So here it has to do more whether it's increasing or decreasing. When the function is increasing, I have an overestimate. When the function is decreasing, I have an underestimate. And it's going to be just the opposite if I did the same thing with a left Riemann sum. I've been teaching this for quite a few years, and I don't have these memorized. I just draw a little picture like this, and it's really easy to see whether they're underestimates or overestimates. But it is nice to know when you're doing these estimates which way it's going to be. Okay? So, let's just finish up this chapter with a couple of examples to see if we understand this trapezoidal approximation, because we've done a lot more with right and left Riemann sums. So, say we have this function, and we're trying to estimate the signed area between 0 and 8 for that function. In other words, find that definite integral. And let's use as our divisions in this trapezoidal approximation at 2, 3, and 6. So at 2, at 3, and at 6. And then we've got our endpoints. We won't do it at 1. So what does this function look like? You don't necessarily need to do that to do the approximation, but at 0, it's kind of hard to graph like that. But if I factor that function, I see that at 0 I get 4. At 2 I get 0. And then it's going to keep going up until I get to 8. When I get to 8, I've got 36. So I'm going to be way up here. This last side is 36. So it's going to be a parabola that looks like this. So our first trapezoid is going to be from 0 to 2. So we can't use the trapezoidal rule because I'm not dividing it up evenly. So the first one is going to be h over 2 times base 1 plus base 2. Well, what are my bases? 4 and 0. And my height from here to here is 2. Then I'm going to have 3 more trapezoids to do. So I can just kind of get my formulas for my trapezoids all set up. So what's the next one? Now I'm going from 2 to 3. Well, if I put in 3, I'm only up at 1. So my trapezoid here is going to be, my height is 1, and my bases are 0 and 1. Well, the next trapezoid goes all the way to 6. If I put 6 in here, I get 16 for that side, and this side is still 1. And the height from 3 to 6 is 3. And the last one goes from 6 to 8. One side's going to be 16, and the other side is going to be 36. Again, you don't have to draw these in. You could have just plugged in the function values. But you kind of see it's concave up, so this should be an overestimate of the exact. So You put all those together, and I think this comes out to be 82. I don't want to spend all the time going through this, waste your time. So I'm pretty sure that that one turned out to be 82. The actual, if we take the antiderivative of that, we get x cubed over 3 minus 2x squared plus 4x. And if we go from 0 to 8, again, it takes a little plugging in. It turns out to be 74 and 2/3. And let's just try the trapezoidal rule. And let's divide it up into 4 equal parts. So we'll still do 4 trapezoids, but we'll use the trapezoidal rule. So if we have 4 equal parts, each one is going to be 2. The first height would be this height, which is 4. Then we have 2 of the next height, which is 0. 2 of the next height, which is 4. 2 of the next height, which is 16. And then only 1 of the last height, which is 36. Okay, so let's actually work this one out. That's going to have nothing, so you have 12 and 32 is 44. So you get 80 times 1, or just 80. So you can see 2 different ways. You could use the trapezoidal rule or just 4 separate trapezoids. They both give a pretty good approximation to our actual. The more trapezoids, the better you would do. Okay, every one that I've given you so far, the trapezoids, or the function has actually been always above the x-axis. So I thought we should do one to show you that they don't have to be. This is estimating definite integrals or signed area, so it can be below. So what does this parabola look like? Well, when x is 0, you get 4. And when x is 2, you get 0. And then, as x gets to be 4, you get down to negative 12. So it's going down like that. It starts here at 4. So can we still do a trapezoidal approximation? Well, this says to use the trapezoidal rule. Now, it doesn't say how many intervals we're going to take. But let's say we take 4 intervals. That divides nicely from 0 to 4. So that would mean that each trapezoid, the h is going to be 1. Well, let me write it this way. Is approximately equal to h over 2. And what is the first side going to be? The first side is going to be 4. Then 2 times the next side. Well, the second side, if you plug 1 into here, you get 3. So 3. And then you have 2 times the next side, but the next side is going to be 0. 2 times the next side, and when you plug in 3, you get negative 5, and then only 1 of the last side. So that last trapezoid is going to look sort of like that, and the last side, when you plug in 4, you get negative 12. So you get 1/2 times 10, and then minus 22. So you get negative 6. That's what we're going to estimate that integral or that signed area to be. There just happens to be more below the x-axis than above. Well, let's actually try to do it. 4x minus x cubed over 3, the fundamental theorem of calculus would do that. When you plug in 0, you get 0. So you get 16, which is 48 thirds, minus 64 thirds, which is negative 5 1/3. So you can see that our trapezoidal approximation did a pretty good job, even though it was below. Now, just to tell you, we might as well, I don't want to pull the wool over your eyes. We do have calculators now. Calculators make approximating these signed areas easier than it was back 400, 350 years ago when this calculus first was formulated. But it's still important to understand these approximation methods because somebody has to work for the companies that are doing these programs on graphing calculators. So they have to decide, should we use trapezoids? Should we use rectangles? The nice thing with calculators is they can do a lot of them. So they could divide from 0 to 5 up into 10,000 rectangles or trapezoids. Anyway, that pretty much ends all the things you need to know about integrals, except the applications of them. So just like with derivatives, it's going to be a lot of fun to learn lots and lots of very practical applications, and we'll do that starting in the next talk. So, take care.